Okay, let's dive in. The idea of finding alien life, I mean, it's captivated people for centuries, hasn't it? It's this ultimate cosmic question.
Absolutely. It fuels so much imagination, so much science.
But the real challenge, it seems, isn't just spotting planets out there. It's figuring out which ones are truly habitable
Right.
and avoiding these things called water world false positives.
Uh-huh.
Planets that look promising because they're covered in oceans, but maybe they're mimicking life signs.
That's the crux of it, yeah.
So our mission today is really to unpack how spotting actual land on these distant rocky worlds could be the key, the missing piece to cut through the noise and really zero in on potential life.
It's a fascinating problem
Mm-hmm.
because these water world false positive, they can be really deceptive.
How so? What's the actual mechanism there?
Well, you get these spectral signatures, the light patterns coming from the planet, and they strongly suggest, okay, this thing is covered in deep liquid water.
Right, which sounds good initially. Water equals potential life.
Exactly. But here's the twist. If the ocean is incredibly deep, we're talking maybe 50 times the volume of Earth's oceans.
Wow, 50.
Yeah, potentially that deep. That much water can actually suppress what we call oxygen sinks. These are natural geological or chemical processes on a planet's surface, like exposed rock, that would normally absorb oxygen from the atmosphere.
Ah, okay. So on Earth, rocks and minerals react with oxygen, pulling it out of the air.
Precisely. But if you cover the entire surface with a super deep ocean, there are fewer places for that oxygen to go. It builds up.
So you end up seeing oxygen in the atmosphere.
And you think, aha,
Yeah.
biosignature, life.
Yeah.
But it could just be a result of the planet being, well, completely waterlogged with no land to soak up the aero, a false positive.
It's like a planetary scale illusion then. These incredibly deep oceans hiding any potential continents or maybe just fractured crust way down below.
That's right. It makes assessing true habitability incredibly difficult because you're looking at what might just be a vast, featureless, very deep body of water, chemically creating a signal we associate with life.
So it really throws a wrench in the works.
It does. And it leads to this critical question researchers are tackling. How can detecting land, actual exposed continents, change how we see these planets? How can it help us avoid being fooled?
We need to look beyond just the water to the world itself.
We need to understand the planet's geography, essentially.
Okay, so this planetary disguise, scientists needed a clever approach. And they think they've found one, right? A way to spot land.
They have, and it's really ingenious. It hinges on using reflected light spectroscopy, basically analyzing the starlight that bounces off the planet's surface.
And land reflects light differently than water.
Very differently, especially across certain wavelengths. The breakthrough finding is that plausible land surfaces, think rocks, soil, that kind of thing, maybe even vegetation analogs, though we're focusing on geology, for now they tend to show a positive sloping reflectance spectrum in the visible and ultraviolet light bands.
Positive sloping, so the reflectance gets stronger at longer wavelengths within that range.
Exactly, the curve goes up. Now compare that to liquid water. Its reflectance spectrum across those same bands is pretty much flat.
Okay, a clear difference.
And even better, ice or snow actually slopes negatively. It reflects more UV blue light and less red light.
So you have these distinct patterns.
Yeah.
Land slopes up, water stays flat, ice slopes down.
Precisely. It gives us a unique spectral fingerprint for continents. Land literally signs its name in the light it reflects back. It's an unmistakable signal if we can detect it.
That's incredibly elegant. And this isn't just theory you mentioned. They're using real data.
Absolutely. The models are built using extensive spectral libraries, like the one from the United States Geological Survey, the USGS. They simulate how sunlight would scatter off different surfaces, though they specifically excluded things like desert sand and ice in some models, just to focus on the general rocky land signature first.
And what kind of telescope do you need to actually pick up this faint reflected land signature from light years away?
Well, that's another exciting part. The analysis, looking at signal-to-noise ratios, suggests that a space telescope with a primary mirror around 8 meters, or about 26 feet in diameter, should be sufficient.
8 meters. That's big, but maybe not unimaginable.
It's definitely achievable. It's comparable to, or perhaps a bit larger than, the Hubble Space Telescope's successor, the James Webb Space Telescope, but this one would be optimized for this kind of visible UV light observation. It sets really important design goals for future missions.
Speaking of future missions, this sounds like exactly the kind of capability needed for something truly ambitious. Is there a specific telescope planned for this?
There is. The big one on the horizon is the proposed Habitable Worlds Observatory, or HWO.
Ah, yes, HWO, the successor to Webb.
Exactly. It's envisioned as the most powerful space observatory ever built. Its goals are huge, multi-wavelength imaging, optical, infrared, and ultraviolet, and it aims to directly image at least 25 potentially habitable exoplanets.
Directly image them, not just detect a dot of light.
Image them well enough to analyze their surfaces and atmospheres. That's the goal.
And HWO would use this land detection technique.
That's the plan. What's really key is the strategy. Integrate these land detection algorithms directly with the search for oxygen biosignatures.
Ah, the dual approach. Check for land and check for oxygen simultaneously.
Precisely. If you see oxygen, but you also confirm the presence of significant exposed land masses that could act as oxygen sinks, well, that strengthens the case for the oxygen being biological.
Because the geology can't easily explain it away then.
Right. But if you see oxygen and the planet looks like a featureless water world according to the reflectance signature, then you'd be much more cautious. It helps rule out those false positives.
So it's about cross-validation, making the evidence robust.
Exactly. HWO, using this dual approach, could potentially give us the first truly unambiguous evidence of life beyond Earth. It's a game changer.
And is this tech ready? Are they testing it?
They are. Early versions of the instruments and algorithms are already being tested on ground-based setups. These demonstrations prove the concept is feasible and help refine the exact specifications needed for the instruments on HWO. The groundwork is definitely being laid.
Okay, so turning back to the planets we already know. Which current Waterworld candidates are scientists looking at now with this new perspective in mind?
Oh, there are quite a few intriguing ones. You've got the outer planets in the TRAPPIST-1 system, which is relatively close at 40 light-years. Their proximity makes them prime targets.
Right, easier to get a good signal.
Then there's the Kepler-11 system, much further out. Kepler-62e and N8-62e are often discussed as potential water worlds around 1,200 light-years away. Kepler-22b is another classic candidate, and GJ-1214b also relatively close.
Any recent discoveries fitting this?
Yes, actually. JWST took a look at GJ-9827d just in 2024. It's about 97 light-years away. They found evidence of a significant water-rich, steamy atmosphere on this super-Earth. It's been called a steam world.
A steam world.
Yeah, its size and steamy envelopes don't neatly fit simple habitability ideas, making it a really interesting test case. Could there be surface features hidden beneath that steam and haze? It challenges our models.
So here's a question for you listening. Which of these planets, or others we haven't found yet, might actually surprise us and turn out to have hidden continents revealed by this technique?
It really forces a rethink, doesn't it? We're closing in on 6,000 confirmed exoplanets now.
6,000. That's incredible.
And among them, over 200 are classified as terrestrial, rocky worlds, and nearly 1,750 are super-Earths. Adding land detection to our toolkit is a huge shift. We're moving from just counting planets to really trying to understand what they're like.
So what's the ultimate vision here? Beyond HWO, how far can we push this surface mapping?
The goal is really to combine everything. High-resolution reflected light spectroscopy, like we've been discussing, coupled with even more advanced tools like sophisticated coronagraph devices that block the blinding light of the host star, and maybe even external star shades.
Star shades, like giant umbrellas in space.
Sort of, yeah. Precisely positioned spacecraft that fly far out in front of the telescope to cast a perfect shadow of the star, letting the faint planet light through. The combination could allow us to move from just detecting spectral signatures of land to potentially mapping exoplanet surfaces in rough detail.
Actually seeing continents and oceans?
That's the dream, transitioning from characterizing atmospheres to direct surface imaging. Using everything we're learning now from the USGS data, the ground tests, and soon HWO to build towards visualizing alien landscapes.
It's just an incredible prospect. Fusing this land detection with the biosignature search, it really feels like we're on the cusp of potentially finding that unambiguous signal of life.
It does feel that way. We're building the tools and the techniques to finally answer that age-old question.
Which leaves us with a final thought to ponder. Will these future telescopes like HWO finally show us continents and maybe, just maybe, something more shining through the oceans of alien worlds?
That's the grand question, isn't it? What will we see when we can finally look that closely?